Welcome back, Houston. Today, we're ready for launch on another beautiful. What is today? It doesn't matter what today is because you can watch this video any day. Either way, we're going to learn about some more energy today. We're going to talk about potential energy, gravity, and one of the most powerful laws in all of physics. I'm basically giving you one of the infinity stones and saying, be careful with this. If you use this improperly, I don't know that anything drastic will happen besides you'll get your problem wrong and then you won't get all the points you want. But you know what I mean? I don't know what you're capable of. You might be able to screw up a whole bunch of stuff with this cool law. But it's powerful nonetheless. It's probably most similar to what are all the infinity stones again? There's the time stone. It's not like the time stone. This one is pretty time independent. What are the other stones? What power stone? We're getting there. It might be most similar to the power stone. What color is that? Lavender? That would be cool. No, this doesn't feel very lavender to me. Whatever the teal one is, it's that one. Okay. So let's go ahead and talk about energy and gravity today. So the first thing we want to ask is, what is potential energy? And how the heck does gravity make this energy or store this energy? Like, what's special about it that the energy is there, right? So the potential energy is I hate this stupid thing. There we go. Okay. Actually, let's not use that color though. What color do you guys want to look at? Green? No, I know. You like pink. Okay. All right. The potential energy is a term used to describe, here's the important part. This is what you want to remember. The amount of work something can do on an object if allowed to. Okay. So there's something about a situation where if I let it, there's a whole bunch of work in the physics sense, as in force times displacement, that can be done to an object. Okay. What we're going to specifically look at today is gravity. And when we raise something up, there's room for it to fall. And while it is falling, we have our weight down. Weight is also known as the force of gravity. So if something is moving in that direction and the weight is in that direction, it's got a delta x and it's got a force, it's doing some work. So if there's room for something to fall, gravity can do work on that object when it's released, right? That's the caveat is this thing can't be like on the surface of the earth because then it can't fall, right? There's an earth in the way. So it has to be raised up and there can't be anything in the way, right? There can't be a shelf or whatever. Or it can be there. It's just there has to be the ability for it to fall. So potential energy is the amount of like stored energy that we put into a system by lifting the thing up so it can fall. And that amount of stored energy is the amount of energy we get out when gravity does its work on that object when it falls. Okay. So maybe let's go ahead and take a look at something and see how, if we can calculate it without being given formulas and all that jazz. And then we'll go back and define some stuff. We'll really hammer out all the wrinkles, but I want to give you like a good visceral, guttural understanding of what the heck I'm talking about. So we're going to determine the potential energy due to gravity. So a student hands their hat on a rack. Not funny. Hangs their hat on a rack. Could you imagine like handing your hat to a rack and your rat's like, oh, thank you. Maybe in the future you'd be like, Alexa, hand me my hat. And then your like robotic hat rat will be like, which one, Tommy? And do you want your Padres hat or your Astros hat or your Cardinals hat today? And then it'll like sort through and give you your hat. That'd be tight. What a time to be alive, you guys. All right. So a student hangs their hat on a rack when they get home from school. Do you guys remember getting home from school in the before times? It's been so long. The hat has a mass of 0.1 kilograms and the rack is 1.3. This should be lowercase m. I'm really sloppy today. Off the ground, meters. How much potential energy does the hat have while on the rack? All right, so let's look at this system, right? We've got our hat rack. It's got some hooks on it. And then here comes you. Apparently you're pink. And you're also wearing a cool backpack. And you got a hat on, most importantly. So you come home and you're only 1.3 meters tall. And you're going to take your hand, you're going to take your hat, and you're going to put the hat on the rack. And then ta-da, it's hanging there. So we want to know how much potential energy does our hat have while it's hanging on this hook. And you're going to say the hook's in the way, it can't fall. Okay, but let's pretend you also have like a cute little puppy dog. This is what dogs look like now, apparently. And your puppy dog knocks your hat off. So then it can fall. Okay. It doesn't matter if it's on something solid, right? The idea is it's not on the ground. That's the important bit. So let's figure out how much gravitational potential energy your hat has. So it's the work that can be done by gravity if it falls. So let's just find how much work gravity does on the hat if it falls. So the work done by gravity is equal to the force of gravity, aka the weight, times the change in position. And in this case, it's probably a y position because we're going up and down, but you know what I mean. If you want your x to be up and down, I'm not going to stop you. Okay, so let's go ahead and plug some of these things in. The force of gravity is weight is mass times gravity. The mass is 0.1. The gravity of weight is 10. And the displacement we're going to fall from here to here, this distance is 1.3 meters. Okay. So 0.1 times 10 is 1 times 1.1. So the work done by gravity when this hat falls and then it's on the ground is 1.3 joules of work. It would be positive because the direction that gravity is applying and the direction that the hat is moving are the same direction. So it's going to do 1.3 joules of work on the hat when it falls. What that means is that the potential energy due to gravity, energy potential, G, equals 1.3 joules. It doesn't have to fall for us to say that when it falls, this much work would be done, right? That's like saying we don't need gun control laws until after someone harms someone else with a gun, right? What a crazy idea, right? Preemptive measures, right? So this energy is how much energy is quote unquote stored in the gravitational field, right? The Earth has like these invisible field lines where the gravity is pulling towards the surface of the Earth. Because you've moved outwards through that field, you have stored somehow some energy. One of the reasons energy is kind of weird is just because it's invisible, right? Like you can't look at a hat and go, it looks like it's got 1.3 joules of energy. You can't tell by looking at something how much energy there is in it. You have to just calculate it. So that's how much energy is stored in our hat when we hang it on a hat rack. Once we allow the hat to fall, we get this energy out. The energy is released and it is turned into energy kinetic in the form of our hat speeding up as it falls and going fast when it hits the ground. So that's how we have potential energy. We could have our hat moving this fast if we let it go. Okay. So now let's go ahead and talk about some formulas. So there is a formula. Let me go back. This is gonna, yeah, wonderful. All right. Let's maybe examine what we did here and then compare it to the formula that you just saw on the other side. The force of gravity is constant, right? Correct. Correct, Mr. Barton. Correct. All right. The force of gravity is weight. It is always the mass of the object times the force of gravity. So this work done by gravity, which equals our potential energy, is equal to mass times gravity every time, because it's always the force of gravity, which is always weight, which is always mg, times the change in position. This change in position, instead of calling it delta x, some people like to just call this h. How high up is the thing before it falls? This is our general equation for the potential energy due to gravity. On some equation sheets, some textbooks, some classes, they like to use a capital U for potential energy. I personally tend to use EG, because E for energy, right? However, mine has the disadvantage of not necessarily reflecting the fact that it is potential energy rather than actual energy. But I don't know. I don't know how big of a drawback that is. If you want to write them EG or UG, I don't really care. Whichever one is better for you. Whatever you like more. Okay. The equation is the mass of the object times G, the strength of the gravitational field on Earth. It's 10 meters per second squared towards the center of the Earth. The acceleration due to gravity. And then H is the distance that the object would be allowed to fall. Let's talk about H for a moment, shall we? Let's say you have... you're digging a hole because you want to, what's the word? Plant a tree, right? And above your hole, you have like some kind of scaffolding, and then you've got like a rope, and then you've got like a little bucket, like that. And then you like raise and lower this thing because you're shoveling your dirt out. Here's you. What do shovels look like? This is fun. I like this. Whoops, hold on. Let's try that one more time. There you go. You're in your hole shoveling, right? You fill this thing up. If we let go of this bucket, how far is it going to fall? The surface of the Earth is our key. Here's whatever. So when we say H, right, we're saying how far can this thing fall? You are a physicist now, whether you like it or not, because you're in the class and you're stuck here, and unless you complain really loud to your counselor, you're not getting out. And they probably won't let you out now anyway because you're too far in. We're almost at the middle of the course. So here are some things. You can say that H equals 0 is the surface of the Earth, right? And then this is, I don't know, 1 meter. And then this is, how far is that? 2, 3, like 3 meters. You could say this is negative 3 meters, right? We've gone below 0, it's negative. Likewise, you could say here h is 0. It doesn't really matter where you say 0 height is, right? If you are saying that the surface of the Earth is 0 height, you can still fall into the negative area. It might be a little more reliable to think of your h as your delta y, change in the vertical direction. So when we do y final minus y initial for the delta, your initial would be 1, your final would be negative 3. Whereas if you say here's 0, this would be at 4. So you have negative 3 minus 1, that's negative 4. You have final is 0, initial is 4, that's still negative 4. The change is all that's important. So as long as you can tell how far the thing moves, that's really all that matters. But some students get a little weirded out when they have to say here's 0, right? So I don't know. Usually it's very nice to say wherever the thing is going to hit is 0, or say this is 0, this is the positive direction, and this is h equals 4. That's another handy one. Usually having a 0 in there somewhere makes your life a little bit easier though, because then you can say here it has no potential energy, right? So just be aware that, you get to pick where 0 is. All right, here's our formula. We're going to use that. Before we use it in like real big kid problems though, there are a couple of like nuanced things that we need to be aware of. And this is the power stone that we were talking about, right? This is the infinity stone that I'm about to teach you. So like kiss your mom goodbye, kiss your dog goodbye, tell them you had a great time taking them for walks every day, but you're leaving a child and coming back a physicist after this slide. So the law of conservation, this is one of the most important ideas in the entire class, in all of physics. Okay, this idea is up there with Newton's 3 laws, Einstein's general theory of relativity, and all that junk, right? This is one of the most important things in physics, and many other physics principles are derived from this idea. I'm trying to tell you it's important. Okay. Unless there is work done on a system from outside the system, the total amount of energy in the system is constant, and energy is conserved. This is called the principle of energy conservation, or the law of conservation. Okay? There are actually 2 conservation laws. There's one for energy and one for momentum that we will learn about later. But these 2 laws of conservation are some of the most important things in physics. Let me show you how to write them algebraically, and then we will see how to use them in a problem. Algebraically, the way we write a law of conservation is the sum of all the energies initially. So if you take your kinetic energy, your potential energy, all the energy at the beginning of the problem, all of that energy will equal all of the energy at the end. The total amount of energy in a system is constant unless there's something outside of the system doing work. Okay. I will show you how to use this momentarily. Let's talk about systems. I have been saying the word system intermittently throughout the class. I said in this system, in this system, in that system, on that system, look at this system. We need to very carefully nitpick the definition of a system right now, because I have seen questions on the AP test like this. Okay. When you do a problem, even if you don't do it intentionally, you are defining a system that you are studying. Okay. Let me show you the importance of understanding how you are defining your system so that we can keep things very clear and separate and distinct in the case of potential energy due to gravity. Okay. So when we have the Earth and you lifting some mass, okay, when we release this mass, we get the potential energy of gravity and it turns itself into kinetic energy. All right. Sometimes no. And you're going to say, what do you mean sometimes no? Why are you telling me this if there's two different ways? How do I know? Here's how you know. It depends on how you define your system. If you define your system as the box only, then when you release the box, an outside force is exerting a force on your box. And because this thing, the Earth, is outside of your defined system, it is doing work on the system. So the work of weight is mg times whatever x is, delta x. Okay. Work is done. You have 0 potential energy here because there is no gravity within the system, right? The thing exerting gravity is outside the system. So inside the system, there isn't a force of gravity. Does that make sense? If you want to use conservation of energy and say that the gravitational potential energy is equal to mgh, then what you have to do is include the source of gravity in your system and say the box and the Earth are within the system. This energy is conserved. Here, work is done by the Earth. Very nitpicky, I understand. Most of the time you won't even think about it. Most of the time you will implicitly assume the Earth is in the system so that we can conserve energy. However, I have seen weird niche cases where they do stuff like this on the AP test. So I just want to bring it to your attention so that you're kind of aware of it, right? Okay, let's do some problems. All right, you're on your roof and you drop a baseball. How fast is the baseball going when it hits the ground if the ball is dropped from 6 meters away from the ground? So here you are on your roof. From here to here is 6 meters. Okay. We could absolutely do this with kinematics and forces. We could say acceleration equals -10, assuming down is negative, meters per second squared. X initial equals 6 meters. X final equals 0 meters. V initial, because we're dropping the ball, is 0 meters per second. And then we could find the time somehow. We could find some velocities. It would be a mess, but we could do it, right? Let's use energy instead. Okay. In this system, we are going to conserve energy. So I am saying that the ball and the Earth are in the system, so that I'm allowed to use conservation of energy. So that tells me the sum of energies initially are equal to the sum of energies at the end of the problem. So let's ask ourselves, what type of energy does this ball have at the beginning of the problem? Well, it is elevated 6 meters above the ground. So this has gravitational potential energy. It's not moving. I'm holding it. I'm going to release it so that its initial velocity is 0. So its kinetic energy is 0 at the beginning. So the only energy we have at the beginning is gravitational potential. Equals, at the end of the problem, our ball is going to fall to the ground. As it falls, it's going to speed up. And as it falls, its distance above the Earth will decrease. So if we look at our gravitational potential energy at the end, mgh, if we say h is 0 here, this is 0 height, then we have none, right? All of our potential energy is gone. We've gotten all the work out of the system that we can. And what happened to that work? What did that work do? It sped our ball up. It gave us kinetic energy. Okay, so our initial energy is gravitational potential because we have an object being lifted above a surface. And our final energy is kinetic energy because we have converted it. It sped up as it fell down. You feel me? You know what you're going on there. So our equation for gravitational potential energy is mgh. Our equation for kinetic energy is 1/2 mv squared. Something that's nice to note here, this mass is the mass of the ball. It's the mass of the object that's floating above the ground. This mass is the mass of the ball. It's the mass of the thing that's going fast at the end, the ball. So because these masses are the same, they cancel. Notice I don't even give you the mass of the ball. It's because it doesn't matter. Now we're just looking for this velocity. So g is 10, h is 6, equals 1/2 v squared times 2. So 60 times 2 is 120 equals v squared. We take a square root, and this is, it's going to be, it's just under 11, right? Because 121 would be 11. It's 10.95 meters per second. Now, we could say that it's negative because it's going downward. It doesn't really matter how you define it. If we say this is h equals positive 6, this is 0, we're getting smaller that way, so negative direction. Something important to note. This is telling you the velocity, not a component of the velocity. It's telling you the velocity. However, it won't ever tell you the sign, right? Technically, when you take a square root in math, you get plus or minus. We would throw one of them away because one of them is just not physical. It's like finding the length of a side of a triangle. You throw away the negative because length can't be negative, right? This one, you have to look at what direction did I say is positive or negative and then fill it in, right? Okay, so there we go. There's our velocity. Not too bad. Energy initial equals energy final. Fill in your energy equations and then solve for the thing you want. All right, let's go ahead and look at a slightly more complicated problem where we'll have more than one type of energy at either the beginning or the final, and then we can see how that affects our problem. Okay. So now we have a plane is dropping a supply crate to some folks in Texas because the roads are too slick with ice. Somehow this got a little funky on me. There we go. The roads are too slick with ice. Global warming, I think. I suspect. It's polar vortex. Who can really say where it came from, though? The crate has a mass of 75 kilograms. Okay. Mr. Barton, why'd you tell us? It's not important. You said in the last problem. Well, hang on. And is dropped from a small plane flying low and slow. 30 meters high at 50 meters per second. Very slow, very low to the ground. The plane is moving perfectly horizontally. When the box is released, how fast will the box be going when it hits the ground? Okay, a couple of things here. First, when we drop this box, it is not just going to drop straight down. It's connected to this plane, and the plane is moving 50 meters per second in that direction. So our box is going to do that. When we say how fast will it be going when it hits the ground, what we are going to find here is this angled velocity. we're not going to find the y component or the x component specifically. We're going to find the total magnitude of the velocity, just so we're clear. Okay. So here's our box. We could use forces, of course. This problem is 100% solvable by ways you already know. However, we're in the energy unit, so let's go ahead and see if instead of looking at the y component and the x component, and then solving for time, and then plugging stuff back in, and then using the Pythagorean theorem to find the magnitude of the velocity, let's see if we can subvert or maybe avoid some of that mathematics that's so troublesome and just get it with energy. So for all energy problems, just like for all force problems, you start with a force diagram and a sum of forces equation. We're going to start with a sum of energy equation. The sum of our initial energy needs to equal the sum of our final energy. And again, we are assuming that the Earth is part of the system. Otherwise, we're not allowed to conserve energy, and Earth does work from outside the system. But nitpicking, not a big deal. All right, initial energy. Well, our box is 30 meters high. Okay, so obviously our box has some gravitational potential energy. Okay. Our box is also attached to this moving plane, so the box is moving at 50 meters per second. So it also has, we'll use capital K, I guess, for kinetic energy. I don't know. Whatever you want. Capital K, E, subscript K, however you like. So it has some kinetic energy at the beginning also. After we drop the box continues to move forward, but it also falls to the ground, converting our potential energy due to gravity. What happens when the box falls? It speeds up, so our gravitational potential energy is converted into kinetic energy. So our final energy is only kinetic energy. Maybe I should put initial and final on here. Okay, now let's go through these equations, substitute them with the equations we know for them, and then plug in some numbers. So gravitational potential energy is mass times gravity times height. Kinetic energy is 1/2 mass times velocity squared equals kinetic energy is still 1/2 mass times velocity squared. This is the final velocity. This is our initial velocity. All right. So we can see you were correct. We have mass, mass, mass. We can divide both sides of the equation by the mass of the box. Mass cancels, cancels. And the mass of the box is unimportant in this problem. What that means is we could drop a crate that is 10 kilograms, 1,000 kilograms, 3 tons. However big this box is, this problem is true for all of it. It doesn't matter. That's, I think, kind of interesting. We are, of course, ignoring air resistance. The shape of the box and the mass of the box affect that in real life. But in our nice high school, safe, sheltered world of like ideal physics, it's not important. So if we simplify our equation, we have GH plus 1/2 V initial squared equals 1/2 V final squared. Okay, I'm really partial to solving for stuff a little. Do we want to? Maybe we'll just plug in. Nah, I don't know. Let's plug in numbers, and then we'll go from there. So G, of course, is 10. At this point, you realize we're not doing physics. We're only doing math. So if you're freaking out, Mr. Barn, this is hard. Math is hard. Physics is not so bad, though. The physics ended on that line. All right. The height, we're 30 meters high, plus 1/2 times velocity squared. Initially, we're going 50 meters per second, equals 1/2 V final squared. So let's go ahead and simplify this side. We have 300 plus 50 squared is 2,500, and half of that is 1,250 equals 1/2 v final squared. So this, adding these, is 1,550 equals 1/2 v final squared times 2 to get rid of the 1/2. That is 3,100 equals v final squared. And then we take a square root with our calculator. Very sneakily, that's probably not a good word to use, but, and we get v final equals 55.68 meters per second. Keep in mind, this is, of course, the magnitude of our velocity. It is moving still at 50 meters per second in the x direction because it's in free fall. There is no acceleration slowing it down in the x direction, so that'll be constant. And then we've gained, of course, some speed in the y direction. So this number that we just calculated, this 55.68, is this right here. And we'd have to use Pythagorean theorem if we wanted to know the y component. But this, here's the stuff we had to do for physics, and then the rest of this is just carefully plugging in numbers. This is much easier, I think, than using the x direction and the y direction, looking at acceleration, solving for times, plugging stuff back in. So hopefully you've thought that this is engaging and informative. Yeah, hopefully it's not too bad. Hopefully you like it. At this point, you can go ahead and hop in the WebEx, ask me any questions you have. Say, hey, Mr. Barton, I didn't really get that stuff about defining systems. And I didn't really, what do you mean conserving energy? You know what I mean? Go ahead and ask me about it. Go be like, hey, Mr. Barton, don't give me the homework yet. I have a question about these now. All right. Until next time, have a wonderful day. Maybe be so kind as to increase those engagement numbers. Give me a little tickle that like button. Maybe even give the subscribe button a little jingle. I'll see you next time.